So this is question 1. 10.2-7, write the state output equations of the system shown in the figure. Okay. So we have 1, 2, 3, 4 state equations and 2 output equations. Let's do the first one. It's going to be Q1 is equal to 1 over S minus lambda 1. There's no input for this, so we don't have any input multiplied by that. So let's find our state bits at that. First, we're going to multiply both sides by S minus lambda 1. We're going to get Q1 S minus lambda 1 is equal to 1. And we're going to get Q1 S minus lambda Q1. As we know, Q of S times S is equal to Q prime, which is equal to 1 plus lambda Q1. That's the state space for the first one.
You're recording a video?
All right. All right, now, since we found the state space for one of them, now we need to find the state space for the other 3. So we have x times such thing. So it's going to be Q2 equal to 1 over S minus lambda 2 times x1. And then we're going to multiply over. We're going to get Q bar 2 minus Q2 lambda 2 is equal to x1. So we get Q bar 2 is equal to Q2 lambda 2 plus x1. All right, that's the second one. And we need to find the other ones if it would let me click. Oh my boy. Oh my gosh. I don't know why I didn't do that for a second. Okay, now let's find the others. Now we know that how the other ones are going to be solved practically the same. Right, so we know that by solving this one, this is going to be Q3 bar, or prime, I'll say Q3 lambda 3 plus, what's the input for that one? X2. And we have Q4 dot Q4 lambda 4 plus x2. These are the 4 state spaces. And then for the output, I'm going to say that y1 is the summation of q1 and q2. So y1 and then y2 is equal to the summation of q2 and q3. And that's how I think you solve number 1. I'm not entirely sure. I will definitely update this problem if it's so very wrong from the answers that my teacher posts. But if not, we're going with it. Okay, the video footage I did earlier got corrupted. So I have to do number 2 all over again. So maybe I can just walk you through my steps. So first we have the questions, right? We have this. This is the question given. We replace the matrices with variables, dummy variables, right? And we know that Q dot is equal to Q prime. So we replace it in the S domain. QS prime is equal to AQS plus BX of S. And we replace the variables in that are matrices with a dummy variable. A, which is a matrix, B, which is a matrix, and C, which is a matrix. And the Q's become Q of S, and the X of X becomes X of S, because we're doing Laplace. We're Laplacing everything. We're going to make everything in the Laplace domain. And if you Laplace anything that's prime, it becomes SQ of S minus its initial condition, usually. But for state space, there are no initial conditions like that, so we ignore that. And nothing changes much over here, right? But we do have this S. Now we need to solve for Q of S, because if we plug Q of S back into here, we can get X of S with Y of S and get a transfer function, right? So to get to this next step, what I do is I subtract a Q of S over, factor out S minus A. We can factor out, no, never mind. We can factor out the Q of S, right? And that leaves S minus A. Why is the I there? Well, S is a scalar, A is a matrix. We need the I to bring S up to the size of the matrix of A, because you can't subtract if they're not equal in size. It's very important. And why is this legal? Because I doesn't actually change the value. It's like multiplying S by 1, but it's making S the same size. But you can't say that this is equal to S. That's not correct. But in a matrix situation, it doesn't change the value of S. And then we divide Si minus A over, and we get this. Then we plug it in to where Q of S is for Y, right? So we get C times what was Q of S is Si minus A raised to the negative 1 times Bx of S. We can divide this X of S over now and make a transfer function. Okay, now that we solve this, we then need to solve this inner part here, because we can't leave it like that. We need to solve the parentheses first. And then we need to do the exponent, and then we can do the multiplication, right? PEMDAS, you know. So we know that the identity for I, is this matrix here, times S. And 1 times S is S, obviously, times 0, blah, blah, blah. That should make sense. Now we can subtract it straight up. It's pretty straightforward how you'd expect it to be. We do S minus negative 1 is S plus 1. 0 minus this 6 over here is negative 6, and so on. 0 minus this 1 is negative 1. S minus 0 is just S. So we know what Si minus A is, but what's the inverse, right? We need to grab that inverse. So coming over to this part, we're using a variable called m raised to the negative 1. The inverse of some matrix is defined as this over here. Now let's ignore this right side. It's pretty simple, but let's not look at that too much just yet. Let's do 1 over the determinant of m. So if we have some matrix, to grab the determinant, we need to do the math. You do cross multiplication, right? So let's say for here, you cross multiply, you get S squared plus S. Then you subtract the cross multiplication of negative 6 and negative 1, which is minus 6, right? You subtract the cross multiplication of one of the other. Sounds weird. Let me do it again. S plus 1 times S minus this diagonal cross multiplication, negative 6 times negative 1 gives a positive 6, but it's subtraction. You end up with this, and that's how we get this here. We put the determinant on the bottom like it does in this formula. And then for this matrix that you see on the right side, you're looking at this one here. You swap D and A. So S goes in the upper left corner, and S plus 1 goes down to the bottom right. And the ones in the corner, -6 and -1, their values get inversed, so they get multiplied by -1 basically. So -6 becomes 6, and that becomes 1. And now we have our basic formula. Okay, now when this is our setup, we've simplified it. Now, what is the order we go for here? Well, it doesn't matter which order we multiply, but for matrix purposes and rules, you cannot multiply a 2 by 2 matrix by a 1 by 2. The reason being is it just doesn't work with the rules, right? You need to have an equal number of rows to the number in the columns, because you need to have S times the first row and then 6 times the second row. Well, if you have S times -2, there's nothing down here, so that you can't do that. So if you do S times -1, you get -S. 6 times 0 is 0, right? That'd be plus 0 on the top. That would be the top term. And then we do 1 times -1, which is -1, plus 0, because anything times 0 is 0, and that's how we get -S, -1 is a result of that matrix multiplication. Then we're going to do -2 times 4, and you'll see after we do that, and also make sure that you keep the multiplication in the right order, because if you don't multiply it any other way, so you put this on the right side, it's not going to give you the same answer. So since the C is on the left side, right, generally you'll have C on the left, B on the right, and whatnot. You need to make sure your matrix results in a scalar, right? So if you have, let's do our matrix multiplication. -2 times -S gives us 2S. And then 4 times -1 gives us -4. You see how this is a scalar? This results in a single term that is not a matrix. And that's what is up top, and that'll be 2S minus 4, S squared plus S minus 6. Now you can inverse this to the time domain, but for this problem, it's not needed. It just wants to know the transfer function. It doesn't state specifically if it wants it in the S domain or the time domain. But if you want to look at my work, I separate the variables. I find a term in the bottom, and then they become hyperbolic cosine and a hyperbolic sine. This is for the time domain conversion. Straightforward. Check my math. This is pretty confident about that. Okay, and for the next part of the question, it wants to know is the zeros in the poles. Zeros reside in the numerator, where it makes it 0, and the poles make it 0 in the bottom. Obviously, if you plug in 2 for S on the top, you'll get a 0, and 2 and -3 by doing the quadratic formula is your hint. I'm sure you can do that. We've done that since algebra. Quadratic formula, pretty straightforward. And whether it's Beebo stable, now there's no imaginary values for the poles. We see we get two real numbers, 2 and -3. Those are going to be on the real axis at 2 and -3. And you see how 2 is in the right side of the plane? We don't want that. That makes it not Beebo stable. It's not good, no bueno. And to whether this is internal asymptotic stability, well, it's the opposite kind of deal for Beebo. The fact that, I think it has the same concept. The fact that it is not a negative number, we have 2. 2 breaks the pattern. See, because if you were to solve this to find a differential equation, right? E to the -3t, as t approaches infinity, t approaches 0. That is what solidifies internal asymptotic stability for poles. The pole must be negative. Now, since 2 is positive, it is not it does not have internal stability. I have not been talking that well. So that catches us up. This might be my fastest video yet. I don't know if me explaining it over my work is decent, but I don't usually do this, but I don't want to go and solve this all over again. Having it written out is pretty nice. Now for question 3, right? Question 3. Simulink question. Oops. Consider a system with the transfer function s plus 3, s plus 2. Okay. So we have said transfer function. This is equal to h of s. Now, the question wants us to determine the observer canonical form for the system. What does that mean? Well, let's see. Now, to observe this, we need to go back to the state space form, which we need to make it a matrix. And how we do that is we need to expand the bottom first. So it's going to be s cubed plus s squared plus s plus 2s squared plus 2s plus 2. S cubed plus 3s squared plus 3s plus 2. Okay, so for matrix A, it's going to be equal to 0, not that big of a matrix. 0, 1, 0, 0, 0, 1, and then for the third term, since this is the third power, right, we're going to have 3 terms starting at s squared. We're going to make it negative. It's going to start from the back. They're all negative from right to left. Okay. And there's a pattern to develop this, and you can look it up. It's something like 0. After the second one, you make it a 1, and all the ones are diagonal going down. And then you start at A1, A2, A3, A1 starting at s squared, A2 starting at s, and A3 being the one without an s. And you make them all negative, as we did. And then for B, it's going to just be equal to, let's see, B will just be the size of 0, 0, 1, just a basic vector. It's just plug in. C is going to be equal to the numerator constants. So we see S is a 1. This goes from left to right this time. 3, and we know that it has to be a 0 because the size of the highest order is 3, so it has to have 3 in there. And a good way to check is that we have A. If we were to multiply A into B and then C, that would result in a scalar, which should be 2s, or s plus 3, which is good. So, and D is just going to be 0. D is usually 0. So, that's part 3. And now we need to do part 3, part A. Now we need to simulate the 0 input response of this realization using Simulink and assuming the initial condition is Q not blah blah blah. How do we do that? For this next part, right, you need to input what we had before into this box as show. Just copy what I've typed in here, pretty much, for the Simulink problem. And then tie it to the scope the output of this to the scope. This is called a state space block. You should find it in the continuous section. To the scope block, the output to the scope, and then you run for 10 seconds, set the time to 10, run, and then your graph should look something like this. I need this. Yes, you should have a graph like this. And you should be starting at 9 because that will be your Y initial spot. Okay? Let me see if anything else needs to be done. Now you can use this MATLAB code. You could probably have chat do this for you. Pop this out. This is the code. And this graph also matches the other. I'm going to snap this as well. For part C, it wants you to compute this another way to prove that it's right, which this also works. And that should be it.